Let's say I gave a statistics test to 2 different classes of 10 students each. Here are the scores for class A, and here are the scores for class B. Now, imagine my boss stops by after class and asks, "Good morning, Prof G. How'd the exams go? How are the students doing?" I could hand him all the exams and say, "Here, take a look for yourself." With only 10 students per class, maybe that wouldn't be so bad. But with more realistic class sizes, he'd probably respond with something like, "Prof G, I don't have time to read all of this. Please give me a summary." And this is really the crux of our job as statisticians. We're not just arbitrarily crunching numbers. It's our responsibility to tell the story of a data set in a way that's accurate and informative to the people who have some stake with that information. My boss needs to understand those results in order to make effective decisions that can affect the lives of real students. And that means we as statisticians need to communicate those results effectively and clearly and honestly so people like my boss can do their jobs as best as possible. So what might we do? One natural place to start is with measures of center, numbers like the mean and median. After all, if someone asks how the classes did, it seems reasonable to respond with something like, the average score was... So let's calculate those. So if we add up all the scores from class A and divide by 10, the number of students, we get 75. And if we add up all the scores from class B and divide by 10, we get, 75. Okay, interesting. Maybe the median will help more. Each class has an even number of students, so we'll order the scores from lowest to highest and find the average of the 2 middle values. For class A, those are going to be 74 and 76, which average to 75. And for class B, that's going to be 60 and 90, which averaged, again 75. So you're telling me both classes had the same mean and the same median? So they did about the same? At this point, if we just stop here, we are implicitly telling a story. We're painting the picture that these classes performed similarly. But that story doesn't feel quite right. Because when we actually look at the data points, when we actually look at the individual student scores, these 2 classes are clearly very different. If I only report the mean or the median, I'm not lying per se, but I'm definitely not telling the whole truth. In class A, almost every score was right around the same value. But in class B, some of the students did very well, while others did very poorly. One class is consistent, the other is much more spread out. And right now, we don't have a number that captures that difference. We have a mean, which tells us where the center is. We have the median, which tells us what the middle value is. And those are both great, but what value tells us how spread out those scores are? Okay, so if our goal is to understand how spread out the data are, one natural question might be, how far away are the scores from the mean? That seems like a reasonable place to start. Can we just take each student's score, subtract it from the mean, and then look at the differences? Let's try it out and see what happens. For class A, the mean is 75. So if we go through, 74 minus 75 gives us -1, and 76 minus 75 gives us +1. For class B, 60 minus 75 gives us -15, and 90 minus 17 gives us +15. Some students are above the mean, those are the positive differences. Others are below the mean, those differences are negative. But this is still a long list of numbers that would be tricky to report if my boss was just looking for a summary. Perhaps we could summarize these values by averaging them too. Let's try it. If we add up all the differences for class A and divide by 10, we get 0. For class B, 0 again. All right, so why? Actually, if we think about it, this does make sense. Now, thinking back to our video on the mean, you might recall that the mean, it's like a balancing point. For every data point that's above the mean, there's another data point that's below pulling it the other way. So when we average the differences, the positives and negatives cancel out. In fact, by definition, this will always happen. So simply averaging the raw differences won't work.
One does not simply walk into Mordor.
All right, but how can we address this then? We need a way to measure the distance from the mean without letting positive and negative values cancel out. Now, one option that we could consider would be to use the absolute value. The absolute value takes negative numbers and returns the positive version. And this could work. It would make all the negatives positive so things don't cancel out anymore. But there is another option that's better, and that's the one that we'll use, which is to square the differences. When we square the differences, this will also make them positive, but it also gives us the added benefit of putting more weight on larger differences, which can be really helpful and really important for data sets that have really large outliers. For example, a value that's 2 units from the mean becomes 4 when we square it, but a value that's 5 units from the mean becomes 25 when squared. That larger deviation now counts for more with 5 rather than 2. Applying this to our example, for class A, the differences were plus and minus 1. Squaring those give us positive 1. For class B, the differences were plus and minus 15. Squaring those gives us values of 225. Now let's try averaging the squared differences. Class A gives us an average of 1. Class B gives us an average of 225. Now we're on to something. We see that distinction here. The consistent class has a small value. The more variable class has a much larger one. There's just one problem. This value of 1 and this value of 225, they're in squared points. But test scores are measured on a scale from 0 to 100. So 225 isn't very intuitive. What does that mean in context of our problem? So we'll take one final step. Specifically, we'll take the square root. This brings us back to the original units, back to the original scale of 0 to 100 points for a test score. We can compute specifically that the square root of 1 is just 1, and the square root of 225 is 15. Now we can interpret this directly. In class A, students tend to be about 1 point away from the mean. In class B, students tend to be about 15 points away from the mean. This final value is what we call our standard deviation. It tells us, roughly, how far data values typically fall from the mean. The larger the standard deviation, the more spread out the data. The smaller the standard deviation, the more it collects around its center. Now, if you've seen standard deviation in a textbook, you've probably seen it written as a formula. It looks intimidating at first, but now you can see that it's just describing the same process we just walked through. Let's approach it piece by piece. First, we subtract the mean. Second, we square the differences. Third, we take the average of them. And finally, we take the square root. The formula isn't arbitrary. It's just a shorthand notation for a very reasonable idea, the process that we just went through ourselves. Good morning, Prof. G. How'd the exams go? How are the students doing? Well, both classes had an average of 75, but Class A had a standard deviation of 1, while Class B had a standard deviation of 15. So one class was pretty consistent, while the other had a much wider range. Precisely. Let me think about some adjustments we could make to possibly help with Class B. And that's why standard deviation matters. It helps us tell the whole story, not just where the data points are centered, but how much they vary. Statistics isn't just about crunching numbers. It's about communicating information as clearly, honestly, and responsibly as we can. I hope you found this video helpful, and I hope you have a great rest of your day.